All right, no time to waste today. Let's get going. All right, so we are going to pick up today where I left off last time. I didn't get to finish this example or start this example, so I'll do that. We will rush our way through angular momentum of system of particles so that I can spend the last 15-ish minutes talking about Monday night. Okay? That's where I'm going. So, last time we got together, we talked angular momentum of particle. We gave angular momentum the letter H. And what else did we say? We said, hey, if it ever focuses. Okay. So we also said it's angular momentum about some point. Just like when you took moments in statics. You took moments about a point. So we had to now, instead of just saying, hey, this is an x or this is y, if I'm taking moments or angular momentum, I got to have this thing located somewhere where I'm taking that about. So that's my point O. We said that this was equal to R cross MV. So if I get a little fancier today, here if we're modeling things as particles, we're going to look at their center of gravity. That's a G. And my R is going to go from this point O to that center of gravity G. So if I had some point O here, here is my blob I'm modeling as a particle. That's its center of gravity. This is my R. R from O to G. And my velocity, depending on how I drew it, maybe I'll draw it this way. That's what we talked about for angular momentum. We had angular momentum impulse principle, where I could say that, hey, my angular momentum at state 1 plus the integral of our moment with respect to time is our angular momentum at state 2. So almost everything we do in this class is 2D. So if you imagine the plane of my paper, my angular momentum in my moments that I'm almost always looking at is going to be in that out of plane direction. So here, I've got some velocity drawn in this plane, R cross V, R cross V. Hey, the angular momentum about O is pointing up. That's the Z direction. Maybe I also applied some moments to this. That moment is curling around in the Z direction. More often than not, there might be some problem where we look at angular momentum in other directions, but for this class, we're almost always interested in the Z. Okay? So for this problem we have, the little one we didn't get to last time. We've got 4 spheres, 5 pounds each, attached to these rigid cross beams. We're going to apply a moment that's a function of time. Half t plus 8, and that's in foot-pounds, so it's a torque. We want to determine the speed of the spheres in 4 seconds starting from rest. So if we look at what we have for our momentum impulse principle, we start here. So initially, we're at rest. Easy. My moment, if I look at top view, I've got these 4 masses, and I'm cranking the moment like this in the Z direction. So My moment's going to be in the z. My angular momentum is going to be in the z direction. This moment as a function of time, that's our angular impulse or impulse of moment. We still got to figure out our angular momentum. And we got to do an integral to figure out what m is. So maybe if we do the impulse first, all we're doing is integrating. So our impulse is the integral of our moment, which is defined as t over 2 plus 0.8. And I want to integrate that with respect to time from 0 to 4 seconds. So t with respect to time becomes a t squared over 2 times 2, so it's t squared over 4. And my 0.8 goes to 0.8 t. That's evaluated at 4 and 0. And this comes out to 7.2. 7.2 watts. Well, this was my moment. And it was given to us in foot-pounds. So, foot-pounds integrated with time, foot-pound seconds. That's half the story. The last one is, what's our angular momentum at state 2? Well, our angular momentum, r cross v, right? That's what I wrote up here at the top. By symmetry, every one of these is going to be the same as the other. So we'll just look at one. So it's velocity. They're all going in different directions, but they're all traveling on that circular path, right? So if I use an r theta system, u hat r, u hat theta. On a circular path, our velocity is purely in the theta direction. So our angular momentum at state 2, we've got 4 spheres, so I'm just going to pull that out front. R, from point O to the point I care about, is just the radius in the r direction, crossed with mass times my velocity. My velocity, I just said, is purely in the theta direction for each of these. So what's that velocity? Just say v in the u hat theta. Cross product, I like to draw a little r theta z triad. Point in the r direction, I cross towards theta, that gives me something in the z. So my angular momentum, 4r m velocity, and this would be my velocity, I could say 2. And this is in the k direction. So we got this thing pretty much finished. We go put our momentum impulse back together. I jump back up here. We already canceled our momentum at state 1. So I really just have my momentum impulse is equal to my angular momentum at state 2. So for us, we said that that was 7.2 foot-pound seconds, that's my momentum, is equal to 4 times rm v2. R, 0.6 feet. mass, English units here. So I got 5 pounds over 32.2 feet per second squared. And my velocity too, which is going to be in feet per second. Calculator, 19.32 feet per second. Hey, that's kind of like the easiest application of our angular momentum impulse principle. I've got something sitting still. Momentum at state 1, 0. I apply a moment as a function of time. Now, can I figure out how fast we're going afterwards? And just like momentum was really good for handling problems that were relating velocity and time, angular momentum is good at handling problems that are angular velocity and time, or in this case, velocity and time. We could easily convert between velocity and angular velocity because we're just traveling a circular path. Velocity is just r times theta dot, or r times omega. Okay? So, unfortunately, that's as easy as it gets. Come on, mouse. Okay, let's make it a little harder, but not too much harder. Old news. I already talked about momentum of a single particle. We talked about momentum impulse for a single particle. And then I'm going to reveal one little half-truth I've told you or thing I swept under the rug. But that'll be coming. So, momentum impulse for a particle. I got the momentum before, plus some moment as a function of time, integrated. I get the momentum after. What happens when we throw a bunch of particles in there? Starts to look pretty gnarly. So if we've got something where I got a system of particles, just like we've always looked at system of particles, we can have external forces and we can have internal forces acting between all these different particles. There might be ropes tying them together. There might be bars tying them together. There might just be some gravitational attraction holding them together. But those are all going to be internal forces. What we want to do is say, hey, I want to make my life easy and forget about those internal forces. We did that for momentum. Can we still do that for angular momentum? So if we think about how we got from linear momentum to angular momentum, we said our sum of forces, mass times acceleration, and we just went like, hey, r cross everything in there, right? So if we still look at this, can we convince ourselves when our forces aren't just external, but they're external and internal forces? So by this figure on the screen here, what about these little guys? All these little ones connecting to their buddies. If I'm at angular momentum, my r is about 0.0 to the center of gravity for these. Can I still get rid of all those internal forces? So I guess the way I draw it, maybe I've got particle 1 and particle 2. They've got an internal force. F12. If I want to think about the angular momentum, I want r cross f. Hey, this is the part that I'm going to start out at. These r's, well, the way I drew them, they look kind of similar, but they could be different. This could be my r1. Maybe my r2 is longer. And that momentum is going to be r cross f, right? Sorry, my moment is going to be r cross f, which we have related to momentum. So my moment for now. So if we look at this and say, well, are these still going to give us the same moments? And even though this guy might not look like its buddy, when we think about what this cross product does, is it takes this force, and all we need to do is figure out that perpendicular distance to this line. And hey, these guys would share that same perpendicular distance. That drawing maybe not so clear. Let's draw a goofier one. Here's particle 1 and particle 2. Keeping my colors consistent here. That's the internal force between them. Now, it's more obvious. R1 and R2, different lengths, right? But the way we calculate moments, we're looking at the perpendicular distance to the line of action of these forces. So I've got the line of action for these forces and the perpendicular distance is shared for them. So the moment that you have from these internal forces, one's moment versus the other moment, they're still going to be the same. They're still going to cancel. So when we do r cross f internal, even though they got different positions, different lengths, I don't have to worry about those internal forces for angular momentum. And that's what this is saying. Let me jump to my half-truth. All right, last time we got together, I said, hey, my moment about O is equal to time rate of change of our angular momentum. And then I said, hey, I can integrate this to get the integral of moment with respect to time is equal to my momentum at state 2 minus state 1, right? We got here, and we move that 1 over, but this is what you are used to seeing for impulse momentum. But now I'm going to tell you that was only kind of true. That was a special case. In general, it's equal to this. V0 of my origin, velocity of my origin, crossed with mass times the velocity at that center of gravity. Oh, what did I do last time that was so sneaky? So last time we got together, I wanted to show you that moment was equal to the time rate of change of angular momentum. So we took angular momentum, and we took its derivative. Right? Angular momentum is r cross mv. I'm going to be a little more careful now. My v, my CG location. My r from O to G. My origin point to my center of gravity. That's the point I'm taking my angular momentum about. So now, if we crush through this a little bit more carefully now, we get the derivative of the first piece times the second, plus the derivative of the second times the first. R dot from O to G crossed with mass times the velocity of g, plus the derivative of the second piece times the first piece. R from O to G crossed with mass times hey, derivative velocity, I'm going to sneak this in as acceleration. Okay? And this is now our time rate of change of angular momentum. So, the second piece, mass times acceleration. Newton tells me with his second law that's F. Force is equal mass times acceleration. R cross F, that guy's my moments. Okay? So part of the story is coming out. My time rate of change is equal to my moments and one extra term. So let's play with this term a little bit and see what's going on. So the term I want to look at, r dot from O to G cross with mass times the velocity of G. R from O to G. Hey, this is a relative velocity. This is the relative velocity of O or G with respect to O. So this term actually looks like the velocity of G minus the velocity of O. So what did I do last time? Last time I said, hey, this velocity, r dot from O to G, is equal to v of G. No, I said it's not. So what was the assumption I made last time? I made this assumption. That velocity of point O was equal to 0. That was the assumption I made. I said, hey, that point that I'm taking moments about is fixed. Boop. And I stopped it. But if that point that I'm taking moments about, O, is traveling around in space, spinning around, all bets are off. I can't use the fact that this term would cancel. I got to track that now. So if I expand this, I would have r dot from O to G, which is this, cross with mass times the velocity of G. I do the cross product of G with itself. I would get v of G crossed m v of G. Something crossed itself, this does go to 0. No lies there. But I got to keep track of this other one. The velocity of O crossed with mass times the velocity of G. This guy doesn't always cancel. So when we put this back together and rearrange, we're going to be left with that equation we started with today. My moments are equal to the time rate of change about point O plus my velocity of O crossed with mass times my velocity of G. This is the full case. Unfortunately, think then, to get to my momentum impulse principle, I want to integrate both sides. Then I got to integrate this nightmare. Right? So that becomes tricky. And this is again, now we look at special cases where this would equal 0. And when those special cases occur, and that does equal 0, we can then integrate this. This part falls out, and I'm back to my momentum impulse principle, and life is good. But for you guys, you really got to do one additional check to make sure that this is true. So, when is this true? Point O is fixed. Velocity is point O is 0. Right? Poof, gone. Point O is point G. I'm taking moments about my CG. If that was the case, something crossed itself. Poof, it's gone. The other one I guess we could get, if point O is fixed, goes away. If point G was fixed, then VG equals 0. Lastly, the cross product between two parallel vectors is 0. So if the velocity of O was parallel to the velocity of G. Case 1, case 2, case 3, case 4. I would say just about every problem that we're going to look at in class is going to fall into one of these categories. Don't think I'm trying to trick you on the exam and going to give you that. So it's just full disclosure. This is what it actually is, and I kind of swept that under the rug last time we got together. So if we have a special case where that second term falls out, then we're back to our good friend, angular momentum impulse. I have my angular momentum before, I crank on it, I get my angular momentum after. In the case we have no external moments, your momentum before is equal to your momentum after. So, now my favorite demo. What does this one look like? Top view. Maybe I've got that problem we just looked at, and it's rotating. I've got some initial R1, and it's traveling, they each have a velocity, v1. But then I change the position of these masses. Maybe I move them in. I shrink it down to where now I have this R2. It's smaller. So if the momentum's the same, because there's no external moments applied, I'm just pulling these guys towards the center. Well, what do we got? I got two balls, and I've got R1 cross mv. My velocity of 1 is R1 times omega 1. And these are vectors, so I'm going to give this a coordinate system really fast. So my R1 is in the R direction. This is in the theta direction. So this would be equal to what's happening at state 2. At state 2, I still have two balls, but now I've got R2 in the R direction plus the same mass, R2, omega 2 in the theta direction. So, come through and look at this. Hey, my 2's will cancel, but these are going to give me momentum in the z direction. M R1 squared omega 1. This one, M R2 squared omega 2. So if I wanted to look at how does this thing change, my m's can cancel. My omega 2 is equal to R1 squared over R2 squared omega 1. As I change that radial position, this thing's going to speed up or slow down, right? So this is what you guys do when you're at your office and you're super bored. I am obviously not a particle. I got mass in the middle. But I can pretend like my hands, if I had like weights, this would be way better. My hands could be these particles. I could start them out here, and I could pull them in. as I'm spinning in this chair, I can't apply any torque in the z direction, right? Because my feet are off the ground. My only torque I can apply is when I start. So I will start, give myself some angular momentum, and then I will move my hands. So, speeding up and slowing down, right? What we're doing is super fun, like a figure skater. Woo. All we're doing is this. I'm taking this mass, and I'm pulling it from the outside to the inside. As I'm changing its position, I'm changing my angular velocity. Now, I usually do that demo in a month and a half when we're talking about rigid bodies, because I'm not just two particles. I got a whole bunch of other things that are still spinning too, right? So my velocity is not going to change this much. It's also going to have some components from the fact that I didn't change my body's center of mass that was rotating about the thing. But the idea is still there. I'm not going to do these problems. I'll just talk about it. So this is a governor. And it uses this exact same idea that I just did there, where I've got these two balls, kind of like what I've drawn, and I'm changing their position relative to their rotational axes. So in this case, collar D is fixed. That one's not going anywhere. But collar C slides up and down. And as collar C slides up and down, moves the balls up and down. So even without applying any external torque to the system, torque in the z direction, you can still change the speed at which this thing is spinning. So if you were trying to control its rate of spin, you want to control how high those balls go. And that's the gotcha here. The one other thing that is nice, if you actually did this problem in full, if you look at the external forces, this is mg coming down. And I just looked at the ball. Maybe I'd have some force going back. And you wanted to convince yourself, hey, this case actually does look like conservation of angular momentum. So what do I need for conservation of angular momentum as this thing is spinning round and round and round? I can have no external moments in the z. So z in this case is vertical. So take a peek. Your r vector, I don't know if I can actually change color than this. Maybe this is my origin, up by point A. This is my r vector. So if I did r cross f or r cross mg, I'm going to get some moments. But there are going to be moments in the out of board direction or moments in the x direction. Right? They're not going to be moments about z. So even though this thing does have some torques happening on it, hey, I'm looking at angular momentum about that spinning axis right now. And if in this case that angular momentum about z is 0, then life is good. We can use conservation of angular momentum. The other thing is, if we think back to this long, boring story I told about moments and time derivative of angular momentum, is this a special case where this v of my origin crossed with mass times the velocity of my center of gravities, will that cancel? Well, in this case, yes, because I'm going to assume my governor is fixed to the ground. And then the point that I'm moving, my O, or in this case A, is fixed. So that has no velocity. That problem is really no fancier than this. Hey, when I'm trying to figure out how the rotational rate's going to change, all I care about is how far off the center line am I pushing these balls. So in this case, if this was my R1, my distance from the center line, I rotated it up to here, this would be my R2. Or if I rotated it down to here, the horizontal to that rotation. That would be that distance that I'm interested in. How far am I pushing things away from that axis of rotation? That all comes out from the cross product. All right. So sorry for rushing you through that. That's not why you came here today, though. All right, 15 minutes talk exam. Statistically speaking, 50% of you bombed the first exam, and I told you I would come up with a solution. I decided it's your problem, you deal with it. No, sorry. What I did decide is I'm going to alter the weightings, and that's going to be up to you. So instead of 25, 25, 25, I'll just set up an algorithm to say that, hey, your two good ones are going to be worth 30, and whichever one you bombed is worth 15. Right? That'll allow you to dig yourself out of that hole faster. So if you bomb the first one, you best not bomb this one, because I'm not doing two. The other gotcha is, once I go through this algorithm for everybody at the end of the semester, I will have some augmented exam average. You know, like, hey, if I just stuck with this, 25s, maybe the exam average is going to be 68. But if I do this, then the exam average augmented would be 72. Right? I'm just throwing numbers out there. I'm going to set 72 as my line between B and BC. Right? And you guys are going to have 25% of your grade that I call the fluff score. Hey, homework. Do you show up to discussion? Do you do the quizzes? Hopefully that 25% is higher than 72. You know, looking at your averages for most of you guys, it's like 95 plus. So that takes this class average and it kind of scoots the whole class average north. That leaves us somewhere with the class average in kind of that middle B range. Right? That is the thinking. The bad part for you is that when you're ready to sit down for the final, like, what grade do I have to get? Well, it's going to depend on how good your buddies are. So you're not going to know exactly how many points you can lose going into the final because you don't know how well everyone else is going to do on that exam. But you can kind of get an idea of where you're going to be. Okay? Any questions on that? All right. So preparing, it's super tiny. Either way, preparing for the for midterm 2, I want to tell you about the sample exams. So probably when you look at the sample exams for midterm 1, you realize that, or now you realize, that a third of those questions were written for work energy. Right? But you can solve them with Newton-Euler, so I went back and I changed them and I solved the solutions with Newton-Euler. That means as you're studying for midterm 2, which now includes work energy, because I kind of shifted around my midterms setup, under midterm 2, I have this little note. Hey, revisit the midterm 1 sample exams and solve those questions using work energy or momentum, if applicable, right? So I made a little list here. The fall of 14 exam 1, number 4. Spring number 1, B, and 4. So don't think that when you look at these midterm 2s, and none of that stuff has to do with work energy, there's not going to be work energy on this exam. Yeah, it is. I just didn't cobble everything together for you, okay? The next thing, my midterm 2 used to also include chapter 6, which we haven't got to yet. So when you read those questions, you'll be like, you never taught us this. Yeah, I didn't teach you that. Settle down. That's coming next week, right? So I tried to, again, skip question 1 and question 4. Those are chapter 6. And those will be on the final. So the same game we have to play. You're going to read parts and it's not going to make any sense. Hey, that's because I haven't taught you that. Move on to the next one, okay? I believe for midterm 1, those problems that I resolved using F equals ma, I believe I left the original solutions for work energy, so they should all still be there. If I'm wrong, I'm bound to get an email. Okay? This mouse is struggling today. Come on. All right. So for midterm 2, room assignments, hey, same as last time. I'll send out an email, but if you forget what that was, it's right there, room assignments, okay? It's got alternate exam, it's got McBurney, it's got the regular exam room. So please look here before you ask. What do you have to know? What do you have to know? All right. So we're primarily focused on chapter 4 and 5. Work energy and momentum methods. Maybe you hate work energy and you hate momentum. Hey, everything I taught you could solve with Newton-Euler. Might not be convenient, and I would highly not recommend it. But you've always got that in your holster, right? That's a tool belt or tool that you already know how to do. Maybe you can solve these problems using things from chapter 3. Maybe it's going to be a 4-page solution as opposed to a 1-page, but that's on you, okay? So use what you know. So chapter 4, work energy. When you read these problems, your first step is to figure out what path you're going to take. A, work energy. This is a shortcut for speed and position. How fast is that ball going after it rolls down the hill? Like, right? That's work energy. Okay? Chapter 5, momentum. This was velocity and time. So, if you want to know something's velocity after a given forcing function or an impact, okay, that's all chapter 5 stuff. I use the term velocity here because, hey, momentum is a vector equation. Work energy, that's scalar. So all the different stuff that we need to know. Work energy, I think you guys are pretty good at this. It's my hope, at least. T1, V1, U12, non-conservative, is equal to T2 plus V2. If you can write this equation, you can piece out all the things you need from it. You're like 80% of the way to the solution, right? So think about what we need to know. I wrote it like this, but for particles, it really can be a summation over all the particles. So your T1 might look like half ma va1 squared plus half mb vb1 squared dot 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 dot. Right? Half mv squared. You might need to relate how is velocity 1 and velocity 2 connected. Maybe they're on a teeter-totter. Maybe there's a string connecting them. Maybe there's a whole bunch of pulleys. But there's probably some more information you can have there if it's a multi-part system. Our potential, remember we got that for gravity? We have that for springs. So for gravity, mgh. For springs, half k delta squared. You are the boss of your datum. Pick it in a way that makes this convenient. You get to decide, hey, I got a ball at the top of a hill, it rolls to the bottom. Do I pick this as my datum, this, or some crazy guy picks the thing in the middle? Right? You could do any one you want. But it's nice to pick either state 1 or state 2 so that you can completely kill one of your terms. Make life easy on yourself. Work. Remember, this is the integral of force dotted with displacement. dot product here. I only care about the force acting in the direction of motion. That's pretty important to us. The other thing, remember, that's what spawned these guys. Our potential energy terms are really just, they popped out of work. But they were special forces. They were conservative forces. Forces where we didn't care about the path, we just cared about where we ended up and where we started. They're forces we saw over and over and over again, so we pulled these out. When you draw your FBD, and it's got mg, force of friction, force of spring, you go two routes. You include all those forces, or you say, hey, these guys are potential. I'm only doing work for the non-conservative forces, a push, a pull, or friction. Right? So a lot of the problems we did, the only time you saw work was from friction. In that case, when your frictional force was maybe dependent on how heavy something was. Maybe the weight was constant. The normal force was constant. Friction force ended up being constant. So this integral, a force over displacement, really simplified to a constant integrated over a distance. So force times distance, right? Like life got a little bit easier for some cases. That's work energy. Power, this was more like a little stop along the way. We had two definitions of power. We said it was a time rate of change of work. So we said power du dt, or force dotted with velocity. Remember when we did this, say we were looking at a motor pulling in cable. We could either look at the force at the motor and the velocity of the cable at the motor, or we could flip that. We could look at the force at the thing it was lifting times the velocity of the thing it was lifting. It didn't matter, right? The power at one was the power at the other, assuming no loss in the middle. Typically, if you had pulleys, you would have triple the force on one thing, but then the velocity would be going a third as fast. So you just kind of trading one another. So the power is still the same. We have efficiency, talked about the input over, or the output over the input. That might be just for the motor, or that might be for the motor and the whole system. You might have some frictional losses from your pulleys that you could lump right into efficiency. Come on now. Particle momentum. We spent a lot of time today talking about angular momentum. Well, it started with particles, right? So for us, I don't know if I can write on this. I can't. Momentum impulse. I've got some velocity before. I add some force over time. I get some velocity afterwards. The key here, remember, this is a vector equation. So what I got in x and what I got in y, what I got in r, what I got in theta, I can split these up and get kind of 2 for the price of 1. It's not just a scalar equation. That's my big gotcha. Impact. We had a little roadmap for how we did these. I got a ball bouncing off a ramp. It's coming in at some crazy angle. First, we wanted to just define our line of impact and plane of impact, right? We did that by saying, hey, how are these guys contacting? What's the tangent surface to both of them? Plane of impact. Perpendicular to that, through the contact point, line of impact. Once we've defined those, we've got different set of equations we can use, and that's what we're showing here. The line of impact equations with system conservation of momentum and coefficient of restitution. Perpendicular to that, in the plane of impact direction, life was easy. Hey, whatever the velocity was before is equal to my velocity after. Right? And maybe this is x and y, so these would be my y directions. Use the right set of equations for your impact problem. You're going to see that. Last thing, My early gift to you, angular momentum. We just talked about that the last 2 days, and it's not going to be on the exam. Yes. I am so nice. So nice. Yes. It'll be on the final. No. So angular momentum, in my opinion, makes a lot more sense and is a lot more useful for rigid bodies. So we introduce it now just so you get a little bit of background of where it came from, and then we'll use it in rigid bodies the last day of class. All right, study hard.